So this is a video going over how to simplify radicals, add and subtract radicals, and multiply and divide radicals. If you know how to do one of those things, like let's say you know how to do adding for radicals, but you don't know how to divide, then just jump to whatever you need help with. So for number one, if I'm looking at something like radical 18, the first thing I ask myself is 18 a perfect square? And well, if I'm listing out my perfect squares, 1 times 1 is 1, 2 times 2 is 4, 9, 16, 25, 36, 49, 64, 81, and so on. Doesn't look like 18's anywhere there. So what we try to do is we break up 18 into a product of factors, where one of those factors is a perfect square. So if I'm thinking about 18 and factors of 18, we got 1 and 18, 6 and 3, and 2 and 9. As I'm scanning through these factors, I notice that 2 and 9 work because 9 is a perfect square. The reason I do that is because if I'm looking at radical 9, radical 9 is asking me, what number do I have to multiply to itself to get 9? The answer to that question is 3. And there's nothing I could do with the radical 2 that's as simple as it gets. So I can simplify radical 18 into 3 times radical 2. For something like number 2, when you've got 216, you need to think a little bit harder. So I don't know the factors of 216 off the top of my head, but I know that 4, if I divide that into 216 in my calculator, I'll get 54. And if I divide, let's see, I could try 9, and I could try 36. So what I do is I just keep trying ones until I get a couple numbers that work. If you don't know how to do that, or if you just don't want to take the time to do that, you can go into y equals in your calculator, type in 216 divided by x, and just go to the table. And that'll give you all the factors of 216. Now I notice as I'm looking at these factors, 2 of those pairs has a perfect square. But what I want to look for when I'm simplifying radicals is the biggest perfect square that goes into it. Just like how when we factor we pull out a greatest common factor, I want to look for the greatest perfect square factor in this case. So I could break 216 up into radical 36 times radical 6, and radical 36 is just 6, and I bring down the radical 6. So radical 216 simplifies to 6 radical 2. Now, if you didn't see that pair of factors and you went with the 4 and 54, it's not the end of the world, because what ends up happening, if you do 4 times 54, you get 2 radical 54. But the problem is 54 isn't in simplest radical form yet. So you'd be able to break 64 up into radical 9 and radical 6. And 2 times radical 9 is the same as 2 times 3, or 6 radical 6. So you get the same answer anyway, but there's just more room for error if you do a process like this. So try to find the biggest perfect square that goes into it. For number 3 and number 4, it's the same sort of problem, only we have a coefficient on the outside. So you ask yourself the same questions. Is 36 a perfect square? Well, the answer to that is yes. So radical 36 is just 6. So this expression is the same as 2 times 6, or 12. So that one we didn't even have to do any work for. Number 3, though, as I'm looking at this, I'm looking at my perfect squares, that 1, 4, 9, 16, 25, 36. And I'm going to try dividing each of those into my 405 until I get one that works. So it doesn't matter where you start. I'm going to start at 49. So 405 divided by 49 is some irrational number, so that doesn't work. 405 divided by 64, another irrational number. But when I get to 405 divided by 81, I notice that I get just an integer as my answer. So this means that 81 and 5 are both factors of 405. Or in other words, when I multiply 5 and 81, it'll get me 405. So I know that's the pair that's going to work for me. So I do the same thing, only I'm going to bring down the 3 being multiplied in front. And I break up radical 405 into radical 81 times radical 5. And again, 9 times 9 is 81, so radical 81 is just the same thing as 9. So now I've got 3 times 9 times radical 5, or 27 radical 5. For number 5 and number 6, the process is the exact same, only we need to watch out for our variable terms now. So I could still ask myself, is 45 a perfect square? The answer to that is no. But if I break it up into 9 times 5, 9 is a perfect square, so that works. And I also want to ask myself, is p squared a perfect square? Well, p squared is just the same thing as p times p, so you can multiply something to itself to get p squared. So p squared is a perfect square, so I could just leave that under the radical. Because radical 9 is going to be 3, radical p squared simplifies to p, because p times p is p squared, and the radical 5 there's nothing I could do with, so I leave that. For number 6, a very similar process, only something with the x third messes things up a little bit. So I could do the same thing, where I bring down the 6 out in front, and I ask myself, is 72 a perfect square? No. Okay, but I know 36 times 2 is 72, and 36 is a perfect square. Then I look at x cubed, and I ask myself, is there anything I could multiply to itself to get x cubed? And if you remember your rules of exponents, I need to add the exponents when I'm multiplying like bases. So this exponent would have to be 1.5 and 1.5 in order for it to make 3, because 1.5 plus 1.5 is 3. So we don't want to deal with any exponents that aren't integers. So what we do is we do the same thing we do the 72 with x squared, where we break up x squared into 2 radicals, one that's a perfect square and one that's not a perfect square. So I'm going to break up x cubed into x squared times x. The reason I do that is because, if I bring everything down, radical 36 is just 6, but radical x squared we already know simplifies to just x. So I'm left with these 2 things that I can't simplify under the radical, and everything's being multiplied. So if everything's being multiplied and I've got 2 things under the radical, I can multiply them both under the same radical and it's equivalent. So my final answer here is 36x times radical 2x. For number 7, I notice 64 is already a perfect square, so when I break that up into radical 64 and something else, I'll be able to just have an 8 on the outside. And m to the 6th is also a perfect square, because m cubed times m cubed is m to the 6th. Notice that any time you have an even exponent for your variable, it'll always be a perfect square. Because if you divide it by 2, so 6 divided by 2 is 3, so you'd get integer exponents for those. So I know m to the 6th is going to be a perfect square. That's going to turn into m to the 3rd on the outside of the radical, because the square root of m to the 6th is m to the 3rd. And then I could do my same trick with the odd exponent. Break it up into n squared times n, and radical n squared is n. I multiply that on the outside. The only thing I have left in the radical is n. For number 8, it's a little trickier to think about, but this x to the 9th here, a lot of people look at that and say, oh, well, that's x to the 3rd times x to the 3rd. But when you multiply bases, remember you add exponents. So x to the 9th actually isn't a perfect square. So let's see what we could do with that. 200 we could break up into radical 100 times radical 2. And I'm going to break up radical x to the 9th into radical x to the 8th times radical x to the 1st. And y to the 6th already is a perfect square because the exponent for that variable is even. So when I simplify this, I get 2 times radical 100 is just 10. Radical x to the 8th, well, what times itself would get me x to the 8th? X to the 4th, because 4 plus 4, when I add those exponents, it would get me 8. And radical y to the 6th is just y to the 3rd. So I look at everything I simplified already. So I took care of that radical, and that radical. But I have this radical 2 and this radical x to the 1st still hanging out. So I could just pop them both under the same radical. When I multiply my coefficients, I get 20 x to the 4th, y to the 3rd, radical 2x. Now, notice for this step right here where I broke up that x to the 9th, I just broke it up into x to the 1st times something else. You're going to do that anytime you have an odd exponent. Otherwise, let's say you broke it down into x to the 4th times x to the 5th. Well, radical x to the 4th is x squared. But radical x to the 5th can be simplified further into x to the 4th times x to the 1st. So if you pick the biggest perfect square that goes into that, and that's just going to be found by subtracting 1 from the exponent, that's going to save you a couple steps. So now we move on to adding radicals. So just like how when we add exponents, or add variables rather, we can only add variable terms if they have the same variable. So along the same lines, we can only connect radical terms if they have the same radical. So I notice 24 and 54 don't have the same radical yet. So I'm going to try simplifying them first to see if I do get the same number under the radical. So I could break up 24 into radical 4 and radical 6, plus I can break up 54 into radical 9 times radical 6. And that's good because if I'm looking at this radical 6 and this radical 6, I want the numbers left under the radical to be the same. So when I simplify, I get 2 radical 6 plus 3 radical 6. And if I add 2 radical 6's to 3 radical 6's, I get 5 radical 6's. Just like when we add variables, if we've got 2x's plus 3x's, we get 5x's. So treat these as the same way you treat variables. So for number 10, I look at my first term. There's nothing I could simplify there. But I could break up radical 27 into radical 9 times radical 3. So I'm just going to rewrite everything else I have. And I know that radical 9 is positive 3. So 3 times 3 is 9 radical 3. And I've got this negative 2 radical 3. Again, they're the same number under the radical, so I can just combine the coefficients, or the numbers out in front, to make 7 radical 3. Number 11. I look at 20, and I say 4 times 5 would be 20, and 4 is a perfect square, so that's probably the best way to simplify radical 20. Radical 18 simplifies into radical 9 times radical 2, again because 9 is a perfect square. And there's nothing we can do with this radical 5 hanging out here. So if I clean this up a little bit, negative 2 times 2 is negative 4 radical 5, plus 2 times 3 is 6 radical 2, minus 3 radical 5. Now I notice I've got a 5 here, and I've got a 5 here. But I have a radical 2 there. Remember that addition is commutative, so I could rearrange things to combine this term with this term without affecting that plus 6 radical 2. So negative 4 radical 5 minus 3 radical 5 is negative 7 radical 5, and I rewrite the plus 6 radical 2. There's nothing more I can do at this step. The radical 5 and the radical 2 are simplified as much as they can be, and they're not like radicals, so I can't add them. Moving on to multiplication of radicals. The rules for multiplication of radicals is that you can multiply the coefficients on the outside and keep them on the outside. So 4 times 3 is 12. And multiply the radicands, or the numbers inside the radicals, and keep them under the radical. So 2 times 18 is 36. Now, once you've multiplied everything, ask yourself if there's anything more you can do to simplify. In this case there is, because 36 is a perfect square. So I could simplify that to 12 times 6, or 72. For number 13, I notice I don't have any coefficients in front here, so everything I multiply is going to be left under the radical in the next step. So I multiply 6 and 12 to get 72, and x to the first times x third is x to the fourth. Again, I look to see if there's anything I can simplify. I know 72 can be split up into 36 times 2. And again, if you have trouble getting those factors, feel free to use your calculator for this. And x to the fourth, since the exponent is even, I notice that it's going to be a perfect square, and I won't have that and under the radical anymore. So this and this are both perfect squares. So I know I'm going to be left with a radical 2, and 6 is what radical 36 simplifies to, and radical x to the fourth is x squared, because x squared times x squared is x to the fourth. So this would be my final answer for number 13. For number 14, notice that I have 7 times radical 3x all squared. Since there are no plus or minuses in here, this represents just one term. So when I square one term times one term is still just going to get me one term. So keep that in mind as you're doing this. You're not going to have to distribute anything for this one. So 7 times radical 3x times 7 times radical 3x. So we do the same thing. We multiply the coefficients. 7 times 7 is 49. And we multiply what's under the radicals. Radical 3x times radical 3x is radical 9x squared. And again, I notice that both 9 and x squared are perfect squares. So this can simplify to 49 times 3 times x. Or 49 times 3 is 147x. For number 15, remember that terms are separated by plus and minus signs. So in my first set of parentheses I have 2 terms, and I'm multiplying that by another 2 terms. So when I'm finished, 2 terms times 2 terms should get me 4 terms when I'm done. So I know for this one I'm going to have to distribute or use the FOIL method. So 3 times 4 is 12. 3 times negative rad 5, well, I know it has to be negative, and the coefficient in front of this radical 5 is just a 1. So 1 times 3 is 3, and I just rewrite the radical 5. Radical 6 times 4 is plus 4 radical 6. Notice I always write the coefficient in the front. And radical 6 times a negative radical 5 is negative radical 30. Since they're both under the radical, when I multiply them, I could keep them under the radical. So I'm looking to see if there's anything I can combine here. Well, if I'm thinking of factors of 30, you got 15 and 2, 3 and 10, 1 and 30. So nothing to simplify here. If these numbers under the radical were the same, I could try to squish these together, but they're not, so I can't get anything going there. So it looks like this is the simplest form for this radical. For number 16, notice the similarity between the 2 sets of parentheses. 3 plus radical 2 times 3 minus radical 2. Anytime you've got two radical terms where the only thing difference between them is one has a plus between them and one has a minus between them, those are called conjugates. And notice how well conjugates multiply when we do it all out. For the last example, nothing simplified, but let's see if something simplifies here. So 3 times 3 is 9. 3 times a negative radical 2 is negative 3 radical 2. Radical 2 times 3 is positive 3 radical 2. And radical 2 times negative radical 2 is negative radical 4. Interesting. So if I'm looking at my terms in the middle here, negative 3 radical 2 plus 3 radical 2 sums to 0. And radical 4 is a perfect square. So this just turns into 9 minus 2, or 7. So anytime you multiply anytime you multiply conjugates, you'll always get a rational number that won't have a radical in it anymore. That's why it's important to remember what a conjugate is in case we need to rationalize something or get rid of the radicals. For number 17, the rules for division work exactly like the rules for multiplication. You divide what's outside the radicals, the coefficients, 8 divided by 4 is 2, and you divide what's inside the radicals and leave them under the radical. 48 divided by 3 is 16. And this simplifies to 2 times 4, or 8. For number 18, notice that there's nothing you could simplify here yet unless we rewrite this as a quotient of two radicals. Because if from here we can go to one radical, we can go backwards and make one radical into two radicals. The reason we do this is because radical 4 simplifies quite nicely to 2 over radical 5. However, we never like to have radicals in the denominator, because if I'm trying to read this as 2 radical fifths, I don't really know what that fraction is. So the way we fix that is by multiplying by whatever is in that denominator if it's a monomial. Because what happens when we do that, on the numerator we get 2 radical 5, and radical 5 times radical 5 is just radical 25. Notice that this simplifies to 2 radical 5, and radical 25 is a perfect square, so that's going to be 5. The reason we do this step right here is because anything divided by itself is just 1. So we're not really changing the value of anything, we're just changing the way it looks. So for number 19, if we're trying to rationalize this one, or get these radicals out of the denominator, remember what we did with the conjugates above, where we just changed the sign in the middle and we got an integer answer. So you could do the same trick for this one by multiplying by 1 minus radical 3 over 1 minus radical 3. When you do that all out, 1 times 1 is 1, minus radical 3, plus radical 3, minus radical 9. I just distributed this binomial to this binomial over 2 minus 2 radical 3. Again, my middle terms cancel here, and in the denominator I'm just left with 1 minus radical 9, or 1 minus 3. So my final answer for this one is 2 minus 2 radical 3, all over 1 minus 3 is just 2. When I divide both these by 2, I get 1 minus radical 3.